Hello everyone, welcome to my channel. In this video I am going to explain PLC, Understanding Programmable Logic Controllers, PLCs. A Programmable Logic Controller, or PLC, is a specialized industrial computer used in manufacturing and automation to control machinery and processes. PLCs are designed to operate in harsh industrial environments and are programmed to perform a wide range of tasks, from simple control functions to complex automation processes. Imagine you're in a car manufacturing plant, and there's a robot precisely welding parts together as cars move down the assembly line. Have you ever wondered how that robot knows exactly when and where to weld? This is where Programmable Logic Controllers, or PLCs, come into play. A PLC is like the brain of the operation, ensuring that the welding robot and all other machines in the factory work together seamlessly. It's a specialized industrial computer that follows instructions to make these processes happen efficiently and safely.
Importance of PLCs in industrial automation.
PLCs are the backbone of modern industrial automation. They provide a reliable and efficient means of controlling and monitoring industrial processes, ensuring safety, accuracy, and efficiency. Without PLCs, many of the industrial systems we rely on today would be impractical or impossible to operate. Consider a water treatment plant responsible for ensuring clean and safe drinking water for a city. The plant relies on a vast network of pumps, valves, and sensors to control the flow, filtration, and disinfection of water. Without PLCs, operators would need to manually control each of these components, which is not only impractical, but also prone to errors. PLCs automate these tasks, ensuring precise control and constant monitoring. This automation not only saves time and resources, but also enhances the quality and safety of the water supply.
Scope and objectives of the lecture.
Throughout this lecture, we'll journey into the world of PLCs, much like the engineers at a power plant who use PLCs to manage the entire electricity generation process. We'll explore how PLCs work, how they're programmed, and the critical role they play in industries ranging from manufacturing and automotive to energy and food production. By the end of this lecture, you'll have a practical understanding of PLCs and how they're the unsung heroes behind many of the products we use in industries we rely on daily. Now, let's move on to the first chapter, where we'll explore the basics of PLCs in more detail.
Chapter 1, Basics of PLCs.
A PLC, or Programmable Logic Controller, is a specialized industrial computer designed to control and automate various electromechanical processes and machinery. It uses a programmable memory to store and execute instructions, typically in the form of ladder logic diagrams, to perform tasks like process control, data acquisition, and machinery operation. The concept of PLCs dates back to the late 1960s when they were developed to replace traditional relay-based control systems. The first PLC, known as the 084, was introduced by Modicon, now part of Schneider Electric, in 1969. PLCs evolved rapidly over the decades, transitioning from fixed hardware to more versatile and powerful programmable devices. Early PLCs had limited memory and capabilities, but modern PLCs are equipped with advanced processors and extensive memory, making them suitable for complex automation tasks.
Key components of a PLC. CPU, Central Processing Unit.
The CPU is the brain of the PLC. It performs the processing of instructions, logic operations, and communication with other devices. It also manages the interaction between different components of the PLC.
Input-output modules. Input/output modules.
Input and output modules are responsible for connecting the PLC to the external world. Input modules receive signals from sensors, switches, or other devices, while output modules control actuators, motors, valves, and other equipment. These modules bridge the gap between the digital world of the PLC and the physical world of the industrial process.
Memory.
PLCs have different types of memory, including program memory to store the control logic, data memory to hold variables and temporary data, and system memory for system functions and data storage. Memory is crucial for storing the PLC program and data required for operation.
Communication ports.
PLCs often come equipped with various communication ports, for example, Ethernet, serial, USB, to connect with other devices, such as human-machine interfaces, MIS, supervisory control and data acquisition, SCADA, systems, and other PLCs. These ports enable data exchange and remote monitoring/control.
Purpose of a PLC in an industrial system.
The primary purpose of a PLC in an industrial system is to provide precise control, automation, and monitoring of various processes and equipment.
PLCs excel in industrial environments for several reasons. Reliability.
PLCs are designed to operate reliably in harsh industrial conditions, making them suitable for critical applications.
Flexibility.
They can be easily reprogrammed to adapt to changes in processes or production requirements.
Safety.
PLCs ensure safe and consistent operation by executing logic and control functions accurately.
Efficiency.
They optimize processes, reduce waste, and enhance energy efficiency.
Data collection.
PLCs can collect and transmit data for real-time monitoring and analysis, facilitating data-driven decision-making. In essence, PLCs serve as the control nerve center of industrial systems, allowing for efficient, safe, and reliable operation while enabling adaptation to evolving needs. This information forms the foundation for understanding PLCs, and you can illustrate these points with practical examples to make the concepts more relatable to your audience during your lecture.
Chapter 2, PLC Programming. Introduce the concept of ladder logic programming.
Ladder logic programming is a graphical programming language used to create control programs for PLCs. It's called ladder logic because it resembles a ladder with two vertical rails and horizontal rungs. In ladder logic, you build control sequences by arranging various symbols to represent control logic, much like you would wire physical relays in traditional control systems.
Importance of ladder logic diagrams in PLC programming. Ladder logic diagrams are crucial in PLC programming for several reasons.
Those are visual representation, ease of use, sequential control, troubleshooting.
Visual representation.
Ladder logic provides a visual representation of control logic, making it easy to understand and troubleshoot.
Ease of use.
It's an intuitive language for control engineers and electricians familiar with electrical schematics.
Sequential control.
Ladder logic excels at representing sequential and parallel control operations, common in industrial automation.
Troubleshooting.
When a problem arises, it's easier to identify and rectify issues in ladder logic diagrams compared to textual programming languages.
The basic elements of ladder logic. Contacts, No/North Carolina.
Contacts in ladder logic represent conditions or inputs. They can be normally open, no, or normally closed, North Carolina. And no contact becomes true, closes, when its input condition is met, while in North Carolina contact becomes true, opens, when its input condition is met.
Coils.
Coils represent outputs or actions. When a coil is energized, turned on, it performs a specific action, like activating a motor or a solenoid valve.
Timers.
Timers are used to introduce time delays into a control sequence. There are two types, on-delay, TON, timers and off-delay, TOF, timers. TON timers start timing when their input condition is true and turn on the output after a specified time. TOF timers do the opposite. They turn off the output after a specified time when their input condition is false.
Counters.
Counters are used to count events or pulses. They come in two types, up counters and down counters. Up counters increase their count when their input condition is true, while down counters decrease their count.
Comparators.
Comparators are used to compare values. They can check if one value is greater than, less than, equal to, or not equal to another value, and they generate an output based on the comparison result.
Example of ladder logic diagrams for simple control tasks.
Example 1. Motor start-stop control. Example 2. Timer delay control. Example 3. Counter control. Example 4. Comparator logic. These examples illustrate how ladder logic symbols, contacts, coils, timers, counters, and comparators are used to create control sequences for various applications.
Chapter 3, PLC Operation.
The scanning cycle of a PLC refers to the continuous and sequential process that a PLC goes through to operate and control a system. It consists of 3 main phases: input scan, program scan, and output scan.
Input scan.
During the input scan phase, the PLC reads the state of all its input devices, such as sensors, switches, and external signals. Inputs are examined to determine their current status, whether they are on or off. This phase ensures that the PLC is aware of the current state of the industrial process.
Program scan.
In the program scan phase, the PLC executes the user-defined control logic, which is typically written in ladder logic or other programming languages. It processes this logic based on the current status of inputs and the previous state of the system. If the programmed conditions are met, the PLC will activate or deactivate internal relays, timers, counters, and other elements to control the desired output actions.
Output scan.
During the output scan phase, the PLC updates the output devices based on the results of the program scan. Output devices include motors, valves, relays, and other components that carry out physical actions in response to the control logic. The PLC energizes or de-energizes output coils to control these devices.
How PLCs process inputs, execute the program logic, and update outputs.
Inputs are continuously monitored and processed by the PLC. When an input's status changes, for example, a switch is pressed or a sensor detects an object, the PLC registers this change. The program logic, created by the programmer, is executed based on the current input states. It follows the ladder logic or other programming language rules to make decisions and control outputs. Outputs are updated according to the control logic. If certain conditions are met, the PLC will energize output coils to activate output devices. If conditions change, the PLC will de-energize these coils to deactivate outputs.
Highlight the speed and real-time nature of PLC operation.
PLCs are designed to operate in real time, meaning they respond to inputs and execute control logic within a very short time frame. The scanning cycle of a typical PLC can occur in milliseconds or even microseconds, depending on the PLC's processing power and the complexity of the program. This real-time capability is essential in industrial automation because it ensures that processes are controlled with precision, minimizing delays and errors. PLCs excel in applications where timing and synchronization are critical, such as assembly lines, robotics, and chemical processes, as they can react to input changes and execute control logic almost instantaneously. Understanding the scanning cycle and the real-time nature of PLC operation is essential for engineers and technicians working with PLCs, as it allows them to design control systems that respond effectively to changing conditions in industrial environments.
Chapter 4, PLC Communication. The importance of communication in PLC systems.
Communication in PLC systems is of paramount importance as it enables the exchange of data and information between the PLC and various devices or systems within an industrial setup. It allows PLCs to receive real-time data from sensors, control actuators, and communicate with other PLCs or supervisory systems. Communication enhances the functionality of PLCs, enabling them to coordinate and synchronize complex processes, monitor performance, and provide valuable insights for decision-making.
Communication protocols used in PLCs.
Modbus.
Modbus is a widely used serial communication protocol that facilitates the exchange of data between PLCs and other devices such as sensors, actuators, and human-machine interfaces (MIS). It is known for its simplicity and versatility, making it suitable for a wide range of industrial applications.
Ethernet/IP.
Ethernet/IP is an industrial protocol that operates over Ethernet networks. It is used for high-speed communication between PLCs, controllers, and other devices. Ethernet/IP provides real-time data exchange capabilities and is commonly used in automation and control systems.
How PLCs can communicate with other devices and systems. Human-machine interface.
PLCs often communicate with MIS, which are graphical interfaces that allow operators to monitor and control industrial processes. The MI receives data from the PLC, displays it in a user-friendly format, and enables operators to make adjustments and send commands back to the PLC.
SCADA, Supervisory Control and Data Acquisition.
SCADA systems are used for monitoring and controlling large-scale industrial processes. PLCs send data to the SCADA system, which provides a centralized view of the entire process. Operators can make decisions based on the information gathered from PLCs and issue commands to adjust the processes needed.
Examples of scenarios where PLC communication is critical: manufacturing assembly line.
In an automotive assembly line, multiple PLCs control different aspects of the process, such as welding, painting, and quality control. These PLCs must communicate to ensure that each step of the production process is synchronized, and any defects or issues are immediately detected and addressed.
Water treatment plant.
At a water treatment plant, PLCs control pumps, valves, and sensors that manage the flow and quality of water. Communication between PLCs ensures that the treatment process is efficient and that any anomalies or emergencies are quickly responded to.
Energy distribution grid.
In an electrical grid, PLCs and substations communicate with each other and with a central control system to manage the distribution of electricity. This communication enables load balancing, fault detection, and rapid responses to power outages.
Logistics and warehousing.
In a logistics or warehousing facility, PLCs control conveyor systems, robotic arms, and inventory tracking. Communication between PLCs ensures that products are efficiently moved, sorted, and shipped.
Oil refinery.
In an oil refinery, PLCs control complex processes, such as refining, distillation, and chemical reactions. Communication between PLCs ensures that these processes are coordinated for maximum efficiency and safety. The importance of communication protocols and the ability of PLCs to interact with other devices and systems is essential for optimizing industrial processes and ensuring smooth operations in various industries.
Chapter 5: PLC Applications. Various industrial applications where PLCs are commonly used. Manufacturing.
PLCs are extensively used in manufacturing industries for tasks such as assembly line control, material handling, and quality control. They ensure precise coordination of machinery and processes, resulting in efficient and consistent production. Automotive. In the automotive industry, PLCs control robots and machines for welding, painting, and assembly. They play a vital role in ensuring the high quality and rapid production of vehicles.
Process control.
PLCs are employed in various process industries like chemical plants, oil refineries, and food processing. They regulate temperature, pressure, flow, and chemical reactions, ensuring safety, consistency, and efficiency in the production process.
Energy management.
Power plants and electrical substations use PLCs for monitoring and controlling electrical systems. They help in load management, fault detection, and power distribution.
Water treatment.
PLCs are crucial in water treatment plants for managing pumps, valves, and chemical dosing systems to ensure clean and safe drinking water.
Advantages of using PLCs.
Speed. PLCs operate in real time, making them exceptionally fast in responding to changing conditions. This speed is critical in applications where precise timing and coordination are essential, such as manufacturing and robotics.
Reliability.
PLCs are designed to work reliably in harsh industrial environments with minimal downtime. Their robust construction and redundancy features contribute to their high reliability.
Flexibility.
PLCs are easily programmable and reconfigurable, allowing for quick adaptation to changes in processes or production requirements. This flexibility is vital in industries where product lines frequently change or where customization is required.
Conclusion.
In this lecture, we've journeyed through the world of Programmable Logic Controllers, PLCs, and explored their fundamental concepts, applications, and significance in industrial automation. Encouragement for further exploration and learning. As we conclude, I encourage you to explore the world of PLCs further. The field of industrial automation is dynamic, continually evolving with advancements in technology. By delving deeper into PLC programming, advanced control techniques, and emerging technologies like the Industrial Internet of Things (IoT) and Industry 4.0, you can contribute to shaping the future of industrial automation. Whether you are a student aspiring to enter the field, an engineer seeking to enhance your skills, or a professional looking to stay at the forefront of automation, PLCs offer a fascinating and rewarding area of study and practice. Embrace the possibilities, keep learning, and stay curious in your exploration of the exciting world of programmable logic controllers. Thank you for watching this video. Please subscribe my channel. Give your comments.